Okay, we're continuing on here, chapter 14 still. So last time we got into another type of titration, and that is a titration of a weak acid with a strong base. And just like previously, we had our base up here in the burette and our acid down here in the beaker, and we're adding as well. And we saw our typical sort of titration curve. Um, and it looks similar to the strong acid, strong base type curve. And just like in that one, we did have our four parts. We had obviously here before we started the titration. And before we started titration, as we talked about, pretty much only have a weak acid in your beaker or flask. And that means that really, you're going to have a sort of a weak acid Ka type of problem that you're going to be doing. We also then talked about the second part of the titration curve, which is again before the equivalence point. And before the equivalence point, you obviously will have a reaction between the base and the acid. You do have to do, as we talked about, an ice table that should be done in moles since we are adding volume, obviously, in this case. And what you should end up with really, when it's all said and done, is you should really end up with a buffer. So remember, this is sort of the part of the titration in this type of titration that you'll essentially make a buffer and then eventually blow through that buffer as you do it. And when you do the calculation here, again, it's sort of up to you how you want to kind of proceed, but you definitely need the first ice table there to be done in moles. You should convert it back to molarity at the end, like we talked about using the total volume. And then at that point, since you do have a buffer, you can either go Henderson-Hasselbalch at that point. You can do a second ice table instead of the Henderson-Hasselbalch. So it's sort of your preference on that point. Here at the equivalence point, we will have a salt that's left over, and this salt will go through hydrolysis because it does come from a weak acid. So essentially, again, here, you'll have to do a couple of ice tables at this point in this type of titration. The first ice table really is to get your concentration of your salt. The second one there is to sort of do the hydrolysis sort of problem at that point. And lastly, here, sort of the fourth part of the titration curve, uh, obviously blown through our equivalence point. And when we do that, obviously in this case, we are just adding excess amount of base, some sodium hydroxide. So we do need to do an ice table to figure out the concentration of your strong base that's left over. And once you do that, you will have the salt that's still there from the equivalence point, and it will go through hydrolysis. But as we talked about, you basically will have a salt that is a base, and you will obviously have the presence of this strong base. And between the two, really the strong base is going to be the major contributor to sort of the pH at this point. So you actually could do a little POH action and then a pH at the end. Any questions on any of that there? All right, so we've now done two different types of titrations. Why not? Let's do a third type of titration. So the next type of titration we're going to talk about is a little bit different than the previous two. And this is a titration of a strong acid with a weak base. Now, the arrangement here is a little bit different. Actually, in this titration, up in the burette is actually going to be the strong acid. So in this titration, we're actually going to be adding acid to our base, and down in the beaker or flask is actually going to be our weak base. So here again, a little bit different in terms of what we're adding. That's also why when we look at our titration curve here, it's sort of upside down, and that is because we are starting with a base. So we're starting at a high pH, and we're adding acid, and we'll end up with a low pH as we continue to add acid. Still sort of that S-type curve, but it's just kind of coming downward. And again, just like the other titration curves, there are those 4 spots before we start, before the equivalence point, at the equivalence point, and then obviously after the equivalence point. So just like we did previously, we're going to talk about, again, what's happening at each of these spots and talk about sort of how you can kind of get through the calculations. So for example, titration where you're using hydrochloric acid to titrate ammonia, which is a weak base. So let's just talk right out here with step number 1, which is obviously before we start our titration here. So before we start or add any HCl, so in this case, the only thing that we have in our beaker or flask is our weak base. So what that means in this particular case is that this would just be a regular KB type of problem, a weak base problem. In this example here with ammonia, it would be ammonia plus some water. Going to make a little ammonium hydroxide. And you can keep the hydroxide together or split it apart. But again, it's going to accept obviously the H plus there. And you would do your initial with your molarities. Again, this would be some minus X's and plus X's. You would go into your KB value. Since this is a weak base, you would solve for X. And again, you just want to keep in mind in this case, though, X is not not the H plus concentration, but it is the hydroxide concentration. So when you do solve for X, you will get the hydroxide concentration, which obviously can then take you to your POH and then to your pH calculation. So very similar to the titration we talked about the other day or the last time. But instead of a weak acid you're starting with a weak base. You're just doing a basic weak base type problem. Again here, because you haven't added any volume or anything like that or started the titration, you obviously could do this just in molarity. You don't obviously have to do moles or anything like that since you have not added any volume. Any questions on that there? All right, so now in this titration, we're going to actually start it up here. So we're going to start here before the equivalence point. So let's take a look and see sort of what goes on at that point. So here we'll go before our equivalence point. And obviously, in this case, we will get a reaction between the acid and the base. And we will have HCl, which is, in this case, again, what we are adding. Reacting with our ammonia, which is what we started with. And it will give us here ammonium chloride, which it is your option. If you want to keep them together, you can. I'm going to just kind of separate them out just so it makes some things easier to see. But it can be NH4Cl together on the other side as well. So again, here we would definitely need to do this in moles since we have started the titration. So just like on the previous examples, I'm just going to make up a starting number and we'll go with the same number there. So we're going to start with 4 moles here of my NH3. And as we talked about previously, since we are before the equivalence point, same rules apply. We know, again, at the equivalence point, the moles of acid and base should equal each other. Since, again, we're before the equivalence point, the moles of the acid, which is what we're adding in this case, should be less, just like it was previously. So, again, just making up a number here, I'm going to go with my 2. Seems like a nice number. And, again, obviously, we have 0. So, at this point in the titration, because the HCl is less moles, it really is like the limiting reagent, and our NH3 is the excess reagent. We've got plenty of it. So once again here, and typically speaking, as we talked about, when you do ice tables that involves moles, a lot of times you do use numbers for the change. Not a lot of times you use X's, but sometimes, but most of the time you don't use X. So here we will use the number, which will be our smallest. And again, you always want to pick the smallest so you do not get negative numbers, which is not good. And you'll end up with 0. We'll end up with 2 moles here and 2 moles here. So like our normal sort of good practice at the end here, once again, we're going to take our total volume and we're going to convert each of these things back into molarity, obviously for both of them. Once again, you could always sort of rely upon your ice table here, provided obviously you write the correct reaction that's going on. But if you did write the correct reaction going on, you could always sort of rely upon your ice table to figure out maybe what's going on at the end here. And if you're not sure sort of what's going on at the end, we do have this guy left over and we do have this guy left over. By the way, why did I ignore chloride? Chloride is, yeah, it comes from a strong acid, so it's a neutral salt, so it's not going to affect anything. So good maybe not to put numbers where you're not going to use them or use them incorrectly. So we already know that's not going to have any effect on the pH, so we don't have to really worry about it too much here in this sort of calculation. So what we do have left, though, that we should worry about are these two guys. And hopefully you could clearly see that they are related to each other. And they are related to each other by 1H plus, which is good. And this has a weak base, as we know, and that would be its conjugate acid, which would make this, once again, a buffer, yeah? So just like the previous titration, you will yield a buffer at this point in the titration. And because it is a buffer that you're left with, and again, this is another illustration like we talked about the other day, that you can make a buffer from a reaction of like a strong base and a weak acid. You could also make a buffer from this reaction of a strong acid and a weak base. Again, the strong acid is not part of the buffer. The buffer is, again, what we're left with at this point here after it's done reacting. That makes the buffer. So again, you could kind of make a buffer from a certain reaction of either a strong acid or strong base with a weak acid or a weak base. Now, because of that, again, probably the easiest move at this point is just to roll into the Henderson-Hasselbalch equation because it is a buffer. R like normal, if you're not fond of that equation for whatever reason, you could just do a second ice table if you want. In this case, you actually have a couple different options. If you choose the ice table route, you could do just a KB table with the NH3 and make sure you have, again, initial on both sides. You could actually do a Ka with the NH4 like a acid, and again, make sure you have the concentrations on both sides. So you have a couple of varieties of ways that you can kind of get there. Any questions on this point? So just like we kind of saw in the previous titration, we will sort of start making a buffer here. And just like we talked about with the other titration, you're continuously adding acid in this case. So again, if you think about sort of the buffer that you make, as we talked about, we have an acid part and a base part, right? If this is the buffer. And obviously in this case, you're adding acid, which means you're just going to keep chewing up, and you probably don't have equal amounts to begin with. As only at a certain spot will have equal amounts. You just keep eating up your acid part of your buffer or your base part of your buffer. And again, eventually you're going to kind of chew through that buffer that you just made. And now as you continue to add acid, now you're adding a lot of H plus, which means we should see a pretty big jump downward in the pH. And that's just like right around here, right? We see that kind of drop in pH pretty quickly, again, sort of vertically as it comes down to the equivalence point. And again, you're going to have some resistance on pH. Then you're going to kind of blow through your buffer. You're going to see a pretty big drop in the pH to the equivalence point, which is what we're going to talk about next here. So let's talk about what happens here at the equivalence point. So at the equivalence point, we obviously still have our reaction, which is not that. We're not using sodium hydroxide here. Again, we are using HCl. All right, so we got our HCl, which again is what we're adding. And we got our ammonia, which is what we started with. And again, we're going to get our ammonium chloride, which once again, you could either separate like I'm doing or keep it together. We'll do our initial here in moles. So we're going to start with 4 moles of NH3. Once again, since we are at the equivalence point, that should mean that our moles of acid should equal our moles of our base. So once again, you should definitely know that that number there should be the same number, and we'll have 0. Change here. Good news is at the equivalence point, you hopefully shouldn't be able to pick the wrong number because they should be pretty much the same number. So we'll go -4, -4, and then obviously +4 moles here. Gonna get us at the equivalence here, 0, 0, and we used up both of those guys. We are left with our 4 moles here of our NH4 plus, and again, taking our total volume, we will convert that back to molarity. Once again, we're not going to worry at all about chloride as it is a neutral salt and is not going to do anything, which also helps us with what's going to happen here perhaps, because what we do have left over is our salt, which is really ammonium chloride. And we have obviously already got rid of the idea of chloride doing anything. So what we have to think about is, will NH4 plus do anything like hydrolysis, since it is a salt? And hopefully you know the answer should be yes, it will, right? Because this again is a weak base, which means this guy came from a weak base and it will react with water because it's going to be relatively strong and go through hydrolysis. And since it does come from a weak base, we know that when it does react with water, it should act as a acid because it came from a weak base, because that means it's a conjugate acid. The definition of an acid is it should donate its H plus over, and you will always make where it came from. And in this case, we will make H3O plus here. So it will continue on to react, which means, again, like we saw in the previous titration, at the equivalence point, you will need 2 ice tables, one to get the concentration of the salt. The second one is a hydrolysis type of ice table. And we also should know a couple of things about our calculation and everything that we're going to do. When I'm done, it should be acidic, basic, or neutral to pH. Should be acidic because we do see H3O plus. Also should tell me when I'm doing my calculation, I should use a Ka, right? So we want to make sure we use our Ka here. And obviously here, we're going to take our, I'll just call it equilibrium here. We're going to take our equilibrium value that we got, and that's going to be our kind of starting amount here. So we'll take from our first table the molarity. And again, as I mentioned before, this is really why it's kind of very important to, after the first ice table, to convert it back to molarity, because you probably don't want to run into this table in moles, because you probably will end up with the wrong answer because you'll forget about the volume part of it. So again, by kind of just converting it back to molarity after the first ice table, you don't have to worry about the units and stuff. You're going to be in the right kind of units to go on to do your hydrolysis. You can just drop it into the next table. We'll go 0 and 0 here. This one is going to be x's. So minus x, plus x, plus x. Equilibrium minus x, x, and x. Once again here, we need a Ka, and we want to solve for x. And in this particular case, x actually does equal the H plus concentration. So once we solve for x, we will have the H plus concentration, which means we could go directly into pH. So in this type of titration, we would expect the equivalence point to be acidic based on what's happening, and the hydrolysis is going to occur with the salt. So we've talked now about kind of 3 different types of titrations. We talked about a strong acid, strong base, and again, at the equivalence point, because you have only a neutral salt left over, you would expect the pH around the equivalence point to be 7. In the titration of our weak acid with a strong base, once again, at the equivalence point, you will have a salt that's left over. And because it comes from a weak acid, we would expect that salt to react with water and produce hydroxide. So we would expect a basic equivalence point pH, not 7, so basic. And here in this type of titration, again, because we have the presence of the salt at the equivalence point, we would expect the equivalence point again, because that salt's going to produce H plus, to be acidic. So you can make a reasonable guess, for example, as to where you should expect the equivalence point to be in terms of its pH. Should you expect an acidic pH, a basic pH, or a neutral pH? And that could be very helpful, for example, if you were doing a titration and you wanted to choose a good indicator to use. So a reminder that indicators work over a specific pH range. So for example, if you were doing a titration like this, where you would expect an acidic pH, you wouldn't want to use one that changes color in the basic range. Like phenolphthalein would be a terrible choice for this one, because your phenolphthalein would have changed way up on top. Yeah, it'd actually go like, kind of like pink back to colorless. Yes. And it was turn colors around a pH of 8, and you need to get to your equivalence point less than 7, right? So that's not going to help you at all. So these are the things you want to think about. Obviously, we're going to talk about indicators in a second as well, but those are things you want to kind of think about is, where you expect your pH to be at the equivalence point. Any questions? All right. So now we hit the equivalence point, not in that one there. All right. We're going to now go past the equivalence point here to the fourth part of our titration. And as we go past the equivalence point, much like other titrations, we're really just adding excess amount of what's in our burette there, right? So we'll have our HCl, which is what we're adding. We're going to react with our ammonia, which is what we started with. And again, going to get our same reaction in this case. Well, NH4 plus and Cl minus. All right, so again here, we're going to start with our 4 moles of NH3. And now we know that obviously we just hit the equivalence point where the moles of each of those guys, the HCl and the NH3, are equal to each other, and that didn't stop us. So we're just going to keep adding some HCl. So now again, past the equivalence point, the moles of what we're adding should be more than what we're starting with. So we'll go with 6 on this one. Why not? Seems like a nice number as well. We'll go 0. Remember, it's at this point that we do get sort of a change in what happens, because we now have less moles of what we started with, the NH3 in this example. It now becomes like the limiting reagent, and the HCl is the excess reagent. So again, here we're going to choose the smaller number, which is 4 and 4 and plus 4. Once again, I'm ignoring my chloride for the same reason as earlier. We're going to end up with 2 moles of our HCl, 0, and 4 moles of our NH4 plus. Going to convert ourselves here back to molarity at this point. And again, that's obviously our total volume, which obviously is the volume of HCl we added plus the volume of the NH3 that we started with, converted to liters, obviously, is how we get to that. And at this point, we do have a couple things left over, really 3, but we're not worrying about that, guys. So we got these 2 things. Once again, is this a buffer? This is not a buffer, yes. So once again, just because you have 2 numbers doesn't make it a buffer. As much as you like to use the Henderson-Hasselbalch equation, it doesn't necessarily mean you should. So definitely not a situation where you should Henderson-Hasselbalch, because it is not a buffer. We really, again, here have kind of 2 acids left over. We have our salt, which is an acidic salt that will go through hydrolysis. And obviously here we have our strong acid. And again, between those 2 acids, if you will, clearly the HCl is going to be a much stronger acid. It is going to be the major contributor to the pH, because frankly, all it needs you to do is open up your burette and drop it into the beaker, right? And it's going to break apart and produce H plus into that solution. So just like we did in the previous titration, we are going to ignore sort of the contribution here of the salt at this point, as HCl should be our major contributor. Because that is a strong acid, that means you most likely already have the H plus concentration, and you could go right into your pH at this point. And we would obviously expect it to be pretty acidic, because basically you're just dropping H plus into that solution really quickly. and we would expect kind of a big drop in the pH. And if we do look at sort of the diagram here, as soon as you hit that equivalence point, you do see that big drop in pH. And that's because you're continuously influxing a bunch of just free H plus at this point, right? Because you're adding that acid, there's no more base there to react with it. So you're just basically dumping straight acid into your solution, going to produce a lot of H plus really quickly. And you're going to see that pretty big drop in the pH past the equivalence point. And again, we kind of see that in the other titrations as well. We kind of get a lot of this OH minus is why it shoots up very vertically at the equivalence point. And it also, in this case, shoots kind of vertically down as well because you get a lot of H plus really quickly. And we see a big change in that pH. Any questions on any part of that there? So why don't we try one here? Let's just say we did this titration and we'll go with what is the pH after 27.5 milliliters of HCl? Actually, 0.1 molar, that'd probably be helpful. 0.1 molar HCl is added to 25 milliliters of 0.1 molar NH3. We'll go with the KB of NH3 is 1.8 times 10 to the minus 5. Seems like a good number. All right, give it a go. I will as well, since I just made it up. We'll see. Let's take a look, see how you're doing. So obviously we're doing a titration, the same one we've been talking about. So again, we do have the HCl up in the burette, and we are adding that to our base here downward. So we obviously can get a reaction here. So same one we've been looking at, which is our HCl plus. And again, that's what we're adding. And our NH3, which is what we're starting with. And again, gonna give us our NH4 plus and our Cl minus. Obviously here we do need to do this in moles. So we can get our HCl moles there by taking 0.0275 liters, which is our 27.5 milliliters converted to liters. Going to times it by the molarity, which is 0.1 moles per liter. They're going to cancel the liters. And that will get us our moles here of, it's going to go into here, 0.00275 moles, right? We'll do the same calculation there, obviously, for our NH3, and in this case, 0.025 liters times our molarity of 0.1 moles per liter here. Again, going to cancel and going to get us 0.00250 moles and 0 here. Any questions so far on that? All right, so obviously here, as we talked about last time, sometimes it's a good idea to know where I'm at in my titration. Where am I in my titration? Am I before? Am I at the equivalence point? Am I beyond the equivalence point? I am after the equivalence point, right? So I am after the equivalence point because I have more moles of what I'm adding than moles of what I started with. So you could always use your ice table and your numbers to figure out where you are. You are past the equivalence point at this stage. Because I am past the equivalence point, I know now this guy is actually going to be kind of like the limiting reagent, as there's not enough moles to handle what's coming in. And that means that it is going to be our base here that's going to be our change. That's going to give us 0 or 6, 0 there. Where you end up here, 0.0025 minus 0.00. No, it's not going to give me a 0 there. Wrong plot. That's going to get me 0.00275 minus 0.0025. That's going to get me number looks very similar. 0.00025 moles. That's going to give me a 0. And 0.00250 moles. Here we're going to find our total volume here. So our total volume, we added 27.5 to 25 milliliters. And that will get us, just to be sure, 52.5, right? There we go. So we're going to convert this back into molarity by taking 0.0525 liters. So again, we got everybody hopefully in the right units. So 0.00025 divided by 0.0525. Gonna get us 0.00476 molar. 0.00250 divided by 0.0525, 0.0476 molar here. So once again, we're not worried about the chloride because it's neutral. We have these two guys left over. And once again, this is not a buffer, right? So we ignore this guy. That means that that's really our H plus concentration, which means that's all we need at this point to go into our pH is minus the log of 0.00476 and like a 2.32. Definitely acidic since we're past the equivalence point and we're just adding acid, right? So we should have a pretty low pH probably. And we're at the bottom part of the curve. Any question about there? So again, we can even take a look since I think this is the titration in this particular picture. And we did 27.5, 2.32. Yeah, it's in between there. So I did pretty good there on that one. Any questions on that type of titration? All right. So for next several minutes, why don't you work through this problem and then we'll start going over some parts of it in a bit. So there's 4 different parts here that we're looking for the pH in this titration. If we took 100 milliliters of 0.1 molar nitrous acid, and we titrated it with sodium hydroxide. We're looking for the pH before we start the titration. We're looking at the pH after we add 80 milliliters. What is the pH at the equivalence point? And what is it after we add 105? So for 20 minutes or so, we'll start working on these guys here, and then we'll start going over it here. So that's obviously before, Okay, so I know you're obviously not done with all the parts, but hopefully got through a couple of them at least, or into a couple of them. So we're gonna start going over the first part or so here, and then we'll finish it up next time. But so let's take a look at this titration here. Obviously, we are adding our sodium hydroxide here to our nitrous acid. And we're going to start with part A, which is really before you start the titration. So once again, in part A, we pretty much just have our weak acid. So for part A, we basically just have our 0.1 molar nitrous acid sitting in our beaker or flask. It has a Ka value of 4.5 times 10 to the minus 4. So clearly, because it is a Ka value, we know that this is really a titration of a weak acid, right? And a strong base titration that we're doing once we start it. But before we have basically now just a weak acid. So to get the pH of our initial solution, we will just do really a Ka type problem. So this will break apart into H plus and NO2 minus. Because we have not really started the titration, we could use molarity here, obviously, in this table. So we'll use our 0.1 molar. These guys will be zeros, and then we'll do our normal sort of X's through here. That means we end up with 0.1 minus X, X, and X. Any questions so far? This is going to go into our Ka expression here. So it's going to be our products over our reactants. And that obviously equals our Ka value of 4.5 times 10 to the minus 4. So popping that in there, you got x squared over 0.1 minus x equals 4.5 times 10 to the minus 4. You could assume x is equal to 0, and because you guys are professionals, you know that that is bad, right? It doesn't work out so well. It's like over 6%. So it is a bad assumption. Also a good reminder to make sure you do check your assumption, right? Just don't assume that it does work. So that's a little quadratic action here for old time's sake. We're going to multiply this over to the other side, and that's going to give us x squared is equal to 4.5 to the minus 4 times 0.1, 0.000045 minus 4.5 times 10 to the minus 4x. Gonna bring everybody back to the other side there. Gonna give me x squared plus 4.5 times 10 to the minus 4x minus 0.000045 equals 0. Gonna give us our A, B, and C here for our quadratic. X is equal to minus b plus or minus square root b squared minus 4ac divided by 2a. So popping in some numbers here is going to give us a negative 4.5 times 10 to the minus 4 plus or minus. We kind of do everything inside the square root there. We will end up with the square action minus 4 times A, which is 1, times C, negative 0.1234. Looks like we'll end up inside before you take the square root of 0.000180 for which if you square root it, looks like it will give us 0.01342, all divided by 2. So going with the positive there, addition, minus 4.5 to the minus 4 plus 0.01342 divided by 2. Going to get us an x value here of 0.006487. Or if we go subtraction here, we know this is not going to be so good because it's going to give us a negative number, which I don't feel is going to be a good solution there. 342 divided by 2. Yeah, so you get something like a negative 0.006935. The reason I know that's not good is because looking at the table, clearly x is equal to h plus, so can't have negative. So this is going to be our H plus concentration. So now we can go into our pH and get our opening pH here. 2 point something, I think, maybe minus log 0.006487, 2.19 to open up the titration with. Any questions on that one there? So again, really just a Ka problem. Couple of good reminders in this step here. Again, make sure you do check your assumption and make sure, again, you do it in molarity here. Again, if you did the assumption without checking, you may get a pH pretty close, but it's not always the case. So make sure you do check it correctly. Any questions so far? All right, so we open up our titration curve here. We are sitting at we're opening up at like 2.19 there. All right, let's take a look here. So we've got a few minutes. We'll do part B here, and we'll see what happens here. We're going to start our titration now. So we are adding, obviously, our base to our acid, and we know it is a weak acid, strong base titration. So we will get a reaction. So we'll take our 100 milliliters and 80 milliliters and see what happens there. So in this part here, we have 100 milliliters of our 0.1 molar nitrous acid, and we've added 80 milliliters of our 0.1 molar sodium hydroxide, if I got that right, I think. Yep. And we still have the same Ka value, 4.5 to the minus 4. So again, since we started titration, we're definitely going to get a reaction. So we'll write our reaction here in our equation. We have our nitrous acid, which is really what we're starting with in the beaker, plus our sodium hydroxide, which again is what we are adding. And that's going to give me a little sodium nitrite on the double displacement reaction and some water in this case. Obviously here, since we're adding, we want to do this in moles. So we'll get some moles here. Moles of my HNO2 is going to be 0.1 liters. That's our 100 milliliters converted to liters times 0.1 moles per liter, which is our molarity. So that's going to get us here 0.01 moles. So we'll go here, 0.01. For our sodium hydroxide, we'll do the same thing. We got 0.08 liters. Again, converting that milliliters into liters there, times the 0.1 moles per liter, which is our molarity. Going to get us 0.008 moles here. So pop that in there, 0.008 moles in this case. So we have 0 of that as well. So am I before, am I at the equivalence point, or am I past the equivalence point? I am definitely before, besides the fact that the next question asks about the equivalence point. But besides that, I do know what I am adding is less moles than what I started with here. So I am definitely before the equivalence point, which means in this type of titration, that should mean something to you. Let's see if it does mean what you think it means, hopefully. So the change here is going to be what we're adding, which is smaller, so 0.008 moles, 0.008 moles, and plus 0.08 moles. That means when we do reach the equivalence point here, we will end up with, looks like 0.002 moles, 0, and 0.008 moles here. Again, we're going to convert back to molarity after this first ice table. So looking at our total volume here, we started with 100 milliliters of the acid. We added 80 milliliters there of the base. That's 180 milliliters. That means each of these gets divided by 0.18 liters, which is our 180 milliliters converted to liters in this case. That's going to get us here 0.002 divided by 0.18, 0.0111, and 444 over here, perhaps. 0.0444. All right, so if you're not sure what is going on at this point, you perhaps already know based on your before the equivalence point in this type of titration, you have this guy left over and this guy left over. Are they related to each other? They are. That is, again, a weak acid and its conjugate base. Like I should have known before I even did the calculation, I should end up with a buffer at this time, right? So again, sort of understanding where you are in the titration should help you when you come to these decisions later on in the calculation. You know, is this like a buffer or not? You should expect it to be. So this is a buffer, which means I'm going to Henderson Hasselbalch that thing. You could double ice table if you like, but why would you maybe want to do that? I don't know. We need the pKa value here, which is minus the log of the Ka. So that's minus log of, we got there 4.5 times 10 to the minus 4. Minus log of 4.5 to the minus 4 is going to give us a pKa of 3.35. So going into our Henderson Hasselbalch, 3.35 plus the log of my base. Hopefully, you know, this one is your base because, you know, that one's called nitrous acid, right? So it has one more hydrogen as well. So we're going to go with 0.0444 divided by 0.0111. So do a little log action of that. Gonna add it to my 3.35. And it looks like right about now in my titration, I'm at 3.95 in terms of my pH, which is good because it went up because I'm adding base. It didn't go below where I started, so that would be bad in this situation. Any questions on that there? So we're at where we got there, 3.95. So we've all jumped up a little here, making our way up our titration curve here. Any questions on that so far? Okay. So obviously we will lay it up there for today.